Hello friends, welcome to GT Science tutorial. In this video, I am going to explain about the Born-Haber Cycle. Born-Haber Cycle is an application of Hess law. It was originally developed to calculate the value of electron affinity, but now we are using this theory to calculate the value of lattice energy. Lattice energy cannot be calculated directly, so we are using the indirect method, that is the Born-Haber Cycle, to calculate the value of lattice energy. In Born-Haber Cycle, we use different other thermodynamic data to calculate the value of lattice energy. Also, this theory is very important for your examination too. So let's start. We know that Born-Haber cycle is used to calculate the value of lattice energy. But what is the meaning of lattice energy? First of all, we need to know that the definition of lattice energy is the amount of energy released when gaseous cation and anion combine together to give 1 mole of an ionic compound. Let me write the definition of it. The amount of energy released when gaseous cation, that is positively charged ion, and anion, that is negatively charged ion, combine together to form 1 mole of an ionic compound. It's called lattice energy. It's called lattice energy. So this is the definition of lattice energy. The amount of energy released when gaseous cation, that is positively charged ion, and anion, that is negatively charged ion, combine together to form 1 mole of an ionic compound is called lattice energy. Let us take an example for this. Suppose we have M, that is metal cation, that is in gaseous state, and non-metal anion in gaseous state as well, and when they combine to give the ionic compound, then some energy is released. That energy is called the lattice energy, that is denoted by U. U is the lattice energy. In many books, you will find lattice energy to be represented by Le. Okay, lattice energy. So it is very simple concept. Whenever a gaseous cation and gaseous anion combine together to form the ionic compound, then some energy is released. Now you might be thinking that why does energy release? So look at here. This is cationic form. This is anionic form. That is highly energized form. Also they are in gas. They are highly energized. Now when they combine, they are in, sorry, this should not be gas, this should be solid. Okay, when they combine, they form solid. That means very stable product. Initially they were very highly energized, but in the final state they are very stable. That is, their energy is low. Where did all the energy go? Yes, that energy is released as a form of lattice energy. We call that energy to be lattice energy. Now let's see the reverse way. There is an ionic compound that is in solid state. Some energy is being added to it and it is converting into the metal cation and non-metal anion. So we can define this lattice energy is in another way as well. So lattice energy can also be defined as the amount of energy required to break 1 mole of an ionic compound into its gaseous cation, that is positively charged ion, and anion, that is negatively charged ion form. So the energy required to break 1 mole of an ionic compound into its gaseous cation and gaseous anionic form is called the lattice energy. You can define lattice energy is any of the way you want. So this is lattice energy. Now let's understand about the Born-Haber cycle. In 1919, two German chemists, Max Born and Fritz Haber, developed this theory to calculate the value of electron affinity. But now we are using that theory to calculate the value of lattice energy. You have already understood what lattice energy is. Now to understand the Born-Haber cycle, we must have the concept of few of the energy terms. So let's understand that so that it will be very easy for us to understand the Born-Haber cycle. First of all, let's understand those terms, okay? Suppose we are taking the example of formation of Mx as a compound. Mx is the ionic compound, okay? So metal in solid state is reacting with halogen or gas non-metal in gaseous state to form an ionic compound, that is Mx. This is in solid state. Now tell me one thing, when they react, is there any exchange of energy? Yes, you are correct. There will be some energy lost, that is represented by del HF, that is called enthalpy of formation. The total enthalpy of formation of the reaction is this much. So some energy will be released when solid metal and gas non-metal react with each other. Okay, now look at here. Suppose if we want to convert this solid metal into gaseous metal, we are trying to convert this solid metal into the gaseous metal form, then we need to supply some energy, that is called sublimation energy. Sublimation energy is the amount of energy required to convert the solid directly into gas, and that is a huge amount of energy. Similarly, if we want to ionize this gaseous metal, that is Mn plus, then we need to provide some energy, that is called ionization energy. You know it already. Ionization energy is required to ionize the metal. That means we are removing an electron. Whenever we want to remove an electron, we need to supply some energy. Now for gas, if this is diatomic gas, we need to convert it into the monoatomic. Suppose if it diatomic, we need to convert it into the monoatomic form. For that, we need to add some energy, that is called dissociation energy. And finally, this can be converted into anion by releasing some energy. It will release some energy. That's why I'm giving minus as the sign. Releasing some energy, that is called electron affinity. If we are adding an electron, then it will lose the energy, okay? If we are adding the electron, it will lose some energy, that is called electron affinity. Now if you understood this much, then let's understand about the Born-Haber cycle. It will be very easier. So let's see. First of all, let me erase this portion. So in this video, we are going to see the formation of three different types of compound: Mx type of compound, Mx2 type of compound, and Mx3 type of compound. First of all, let's understand about the formation of sodium chloride. This is Mx type of compound. Why Mx? There is one metal, one non-metal. So the reaction will be like this. Sodium is in solid state, will react with chlorine in gaseous state, and it will form what? What will it form? Yes, you are correct. NaCl, sodium chloride in solid state. While undergoing this reaction, it will lose some energy, that is called enthalpy of formation. So you understood this method. But His law says that this reaction will not happen directly, but there will be a set of other reactions, small reactions, that will lead to the product. So first of all, what will happen? This sodium in solid state will convert into the gaseous state. Sodium in gas. So which energy should we provide? Yes, you are correct. Sublimation energy. That is positively charged, positive, because we are giving the energy. If we are giving the energy to the system, then its sign is plus. If the system is losing energy, then its sign will be minus. Now, it won't react only in gaseous state. It needs to be ionized as well. So we are ionizing it. So it will be Na plus in gaseous state. For that, we need to provide the ionization energy. You understand this correctly? Yes. Now look at here. To balance this original reaction, we have to put 1 by 2 over here, because there are 2 chlorine and we need only 1 mole of the 1 mole of the product. That's why we can't put any number over here. That's why we are dividing the Cl2 by 2. Then we need to convert this into monoatomic form. Then we need to provide some dissociation energy, but there is only half of the energy required, so we'll put half over here. This is in gaseous state. Okay, this is already in gaseous state, that's why we are not providing any sublimation energy over here. Now this chlorine needs to be ionized as well, that is Cl minus. Now we are giving 1 electron to it. This electron, the electron lost by the sodium, will actually go here, and it will combine with the Cl. It will go in the last orbital of Cl and it will gain the electron, and as a result of that it will lose some energy, that is called electron affinity. That's why the sign is minus over here. So I hope you understood this much. Now we know that in gaseous state the sodium ion and chlorine ion will react with each other as well, and it will form sodium chloride in solid state. In this method it will lose some energy, that is called lattice energy, losing energy. That's why we have given minus sign. Now we need to write the final expression. Therefore the final expression will be, according to Hess law of constant heat summation, the total heat energy required for the conversion of reactant into product will be equal to the algebraic sum of all the energy term in all the steps. So the final energy, the total energy is this much minus del HF will be equal to how much? The algebraic sum of all the energy terms in all the steps. So it will be sublimation energy, its sign is plus ionization energy plus half dissociation energy minus electron affinity, finally minus U, that is lattice energy. This is the mathematical expression that is used to calculate the value of lattice energy. We can rearrange this equation to write this. U will come this side and it will be equal to Se plus Ie plus half dE minus Ea plus del HF. This will go this side and its sign will be plus. So this equation is used to calculate the value of lattice energy. Now you can see over here there are total 6 terms. 1, 2, 3, 4, 5, 6. In examination for numerical problem, it might give you any 5 term and it will tell you to find the value of the 6th term. So you don't have to do a lot of things. You just have to put all those values in this equation and find the required value. So this is very simple, right? This is the MX type of compound. Now let me teach you the MX2 type of compound. For this, let me read this portion. For the formation of MX2 type of compound, we are taking the example of formation of magnesium chloride, that is MgCl2. There is one metal Mg and 2 chloride ion, that is Cl2. Now let's see how this reaction happens. So magnesium in solid state will react with chlorine in gaseous state to form magnesium chloride, right? We don't have to balance it because it is already balanced. Some energy will be released in this initial state, main step, that is called the enthalpy of formation, right? Total heat content of the system. Now look at here, we will follow the same method. This solid, first of all, will convert to Mg gas by absorbing some energy, that is called sublimation energy. Now we need to provide some energy, ionization energy, to convert it into the ionic form, that is Mg plus. But tell me one thing, is the valency of magnesium 1? No, its valency is 2. That means we need to eject one more electron. So we need to provide more ionization energy, that is ionization energy 2. Let's consider this to be 1. More ionization energy to convert it into Mg2 plus, that is the gaseous state, right? Now similarly for chlorine, look at here. Do we have to divide here by anything? No. So if we provide the dissociation energy, then this diatomic molecule will convert into the monoatomic, that is Cl. Now there will be 2 Cl because there are 2 Cl, and this is now a monoatomic molecule, monoatomic form, right? So this is in gaseous state again. Now we need to provide when if we want to convert this in this Cl gas into Cl minus, then we need to provide some ionization, some energy is released from there, that is called electron affinity. Now 2 electrons are being converted to anionic form, that's why there will be 2 times of electron affinity required for this method. Now finally we got this much. Now look at here, we have Mg2 plus, we have Cl2 minus, 2 Cl minus. Now they will finally react to form MgCl2, and some energy will be released over here, that is lattice energy. Now according to his law, we can write the mathematical expression for this method, that is minus del HF will be equal to how much? Look at here, Se sublimation energy, its sign is plus plus plus. So IE1 plus IE2, as both of them are ionization energy, I am writing them in bracket. Then there will be plus dissociation energy minus 2 electron affinity will and minus U. This is the final mathematical expression for MX2 type of ionic compound. Look at here, how many terms are over here? 1, 2, 3, 4, 5, 6, 7. In the first case, that is MX type of compound, there was only 6 terms. In this case, there are 7 terms because there are 2 ionization energies. In the examination, if it gives you only the ionization energy of magnesium, that means it is giving the combined form IE1 plus IE2. Otherwise, it will give you both the values separately. So among these as well, it will not give the value of 1 and rest of the values will be given. You need to find the other value by using this formula. But to know that, you need to know how to make this chart or how to make this cycle. Okay. Now let's see one more type of compound, that is MX3 type of compound. For that, let me erase this portion. Okay. MX3. Can you tell me an example of MX3 type of compound? Yes, you are thinking correct. That is aluminium chloride. An example of that is aluminium chloride. Let me read this portion too. Okay. So we are taking another compound, aluminium chloride, and this is MX3 type of compound, right? So the reaction will happen like this. Aluminium in solid state will react with Cl2 in gaseous state, giving AlCl3, right? AlCl3 is the form. Now we need to balance it. Without balancing it, we can't write it, right? So we need to divide it by 2 so that it will be converted to monatomic form. But there are 3 chlorine, so we need to put 3 over here. Finally, this reaction is balanced. This is in solid state, and the heat energy that is released in this method is called del HF, enthalpy of formation. Now let's see the individual steps in it. Al will convert to Al gas form by getting sublimation energy. Now this will lose 1 electron, it will convert to Al plus, and that is IE1. The energy gained by it is IE1. IE1 means ionization energy 1. Again, it will gain some more energy, that is IE2, to convert it into Al2 plus form. But the valency of aluminium is 3. So we need to remove 1 more electron from here. So we need to provide little bit more energy, that is IE3. So finally, it will be converted to Al3 plus. But in this case, you can see over here, this is already in gaseous state. So do we have to provide sublimation energy? No, not at all. We need to provide some dissociation energy. How much dissociation energy should be provided? 3 by 2, right? So it will convert into 3 Cl minus ions, and this is also in gaseous state. And finally, it will release some energy, that is electron affinity, 3 times electron affinity to convert it into 3 Cl minus form. This is also in gaseous state. And finally, these two will react and form AlCl3 in solid state, and the energy released is minus U. Now let's form the final mathematical expression over here. Minus del HF will be equal to, look at here, minus del HF will be equal to how much? Se plus IE1, IE2, IE3, right? IE1 plus IE2 plus IE3 plus 3 by 2 dE minus 3 EA minus U. This is the final mathematical expression for this method. You can see over here there are 8 terms now. 1, 2, 3, 4, 5, 6, 7, 8. But these 3 are all ionization energy terms. That's why I have written them inside the bracket. So in examination, if MX3 type of compound is saying, then it will give the all the values except one value. If it gives you only the ionization energy of aluminium, that means it is given the combined value of IE1 plus IE2 plus IE3. Okay, and it will otherwise it will give you the individual values, and it will give all the other values except one value. You need to find the value of that required data, so that you'll get the full marks in the examination. Now see, this is MX, MX2, MX3 type of compound. We're very simple. But there is one more example that where we need to think little bit. Let me write that. Let me show you that example. But before that, let me edit this portion. And that one example is very important for your examination as well. So please watch this, watch that example completely and understand that properly. The Born-Haber cycle for the formation of magnesium oxide or calcium oxide is a little bit different than the other examples. Let's see how we make the Born-Haber cycle for the formation of this compound. So let's see the reaction. Magnesium in solid state reacts with oxygen in gaseous state to form magnesium oxide. This is in solid state as well. Now some energy is released, that is called enthalpy of formation. As the energy is being released, we are putting minus sign over here. Now this solid needs to convert it into gaseous first of all. Now to convert into magnesium gas, it will need some energy. That energy is sublimation energy, and the sign is plus because we are providing the energy to the system. Now again, this magnesium needs to convert into the ionic form, so it will lose one electron to convert into Mg plus, and for that it will need some energy, that is ionization energy 1. But the valency of magnesium is 2, so it will lose one more electron to convert into Mg2 plus form, and it will need more energy, that is IE2, and finally it converts to Mg2 plus gaseous ion, and it is ready for the reaction. Now look at here, to balance this reaction we have to put half over here because we can't put any number over here, right? Now it needs to convert, it is in diatomic form right now, we need to convert it into the monoatomic form. So to do that we need to provide dissociation energy, and there is half return, so we'll need only half of the dissociation energy, and it will convert to O, that is in gaseous state. Now we need to convert it into the anionic form, that means it needs to gain electron, and as a result of that it will lose some energy, that is called electron affinity. Till this much it is completely similar. But what is the valency of oxygen? Yes, you are thinking correct. The valency of oxygen is 2. That means it will have O2 minus form in the last. And to convert O minus into O2 minus, it needs to gain one more electron. When it gets one more electron, it needs to lose some more energy, right? The reaction should happen like this, but no, it doesn't happen like this. So look at here, when it gains one electron, then in the electronic cloud there is one extra electron over there, and as a result of that there will be certain force of repulsion. Okay, and if we want to add one more electron, then what will happen? Those electron cloud will try to repel that incoming electron from there, and as a result of that we need to supply some energy from outside to put that electron into that orbital. That's why we need to provide this much of energy in the second case. Okay, so be careful. In the first case some energy is being released, in the second case we need to provide in order to put that electron into the outermost orbital because of the electron cloud repulsion. So finally Mg2 plus and O2 minus are ready for the reaction, and when they react they form this MgO, and some energy is released, that is called lattice energy. Now the final expression for the Born-Haber cycle for the formation of magnesium oxide will be how much? Minus del HF is equal to Se plus IE1 plus IE2 plus half dE 1 by 2 dE. dE means dissociation energy, minus EA1, this is 1, this is 2, okay. EA1 plus EA2, you have to be very much careful over here, and finally minus U. This is the final expression. This is the final expression for the formation of magnesium oxide compound according to Born-Haber cycle. Now, in this case also, all the energy terms will be given except for one energy term, and you have to be very much careful over there, like over here, okay, EA1 and EA2. If in the examination this question is given, then be very much careful. Not all the electron affinity is subtracted. Second electron affinity will be added. So be very much careful over there. So this is little bit different than the other example. So I hope you understood this example very nicely. So that's all in this video. I hope you understood everything about Born-Haber cycle. In my next video, I'm going to explain some numerical problems related to this Born-Haber cycle. And if you like the video, please share this video as much as you can. And thank you for watching the video.